a short video on one additional aspect about first-order linear differential equations. So we want to look at a special case where this circumstance comes up, the constant coefficient case. So dy dt equals a constant times y plus b of t. And even more than that, we're going to specialize even further. We're going to assume that a is a negative number. And something a little bit interesting happens when we have that situation, when we have a constant coefficient linear differential equation and the constant is a negative number. I'll explain this through an example. So here's such a differential equation. See, our a is -1/2. Okay, now we're going to solve this using the linear principles, not the integrating factor. So if we do that, we look for the homogeneous solution first. So there's the associated homogeneous differential equation. And with constant coefficient, we know this is very easy to solve. It's c times e to the -1/2 t. And this is the thing, if you have a negative a, you will get a negative exponential for your homogeneous solution. Alright, so that's actually going to be the main point of what I want to say, but let's complete this problem so that we can see it happening very concretely. So the next thing to do is to find a particular solution to the non-homogeneous version. So I'm going to bring the -1/2 y over. Okay. I am going to guess a solution, because I have 3 sine t here, I'm going to guess that there'd be a solution that would work that would be something times sine t plus something times cosine t. So alpha and beta are my undetermined coefficients. If I do that, here's my derivative. And then I'm going to plug it in and see what the alpha and beta have to be. So dy dt plus 1/2 y equals 3 sine t. Okay, so I see that my sine t's have to match up. So it looks like 1/2 alpha minus beta is going to have to equal 3. And then the cosines, my alpha plus 1/2 beta, I don't have a cosine on the right, so those have to add up to 0. Alright, so I have to do a little bit of algebra to solve these two. And let me just fast forward that. Let me just tell you what the result is. The alpha comes out to be 6/5, and the beta comes out to be -12/5. Which means that my particular solution is 6/5 sine t minus 12/5 cosine t. Okay, which means then that my overall general solution is that plus my homogeneous solution. That's the one that has the c in it. That's the piece, that's the term that allows me to solve for any initial condition. Okay, but there's the general solution. Okay. And let me just say that in general, right, so if a little more general than this particular example, our particular solution is whatever it is, and then we'll have plus c times a negative exponential. We'll always have that negative exponential term if we have one of these linear differential equations with a negative a. And I want to point out the behavior of such a function. And here it is, and this is what I want to say. The negative exponential, of course, negative exponentials, as t goes to infinity, those get smaller and smaller, exponentially, right? They decay exponentially. So this term is going to become negligible pretty quickly. All right, so what that means is that in the long run, this function will act like just that particular solution. The homogeneous piece kind of goes away. It doesn't matter pretty soon after t equals 0. What's also interesting about that is, remember that the initial condition is going to determine the c, and the c is on that piece that's going away quickly over time. So evidently, information about the initial condition goes away. In other words, this function kind of forgets where it started, and it just settles into this function. It just wants to be this function, sort of regardless of where it starts. This is the function that kind of persists over time, and yes, in the beginning, different initial conditions will start differently because of this piece, but that piece dies away. And this phenomenon, and what's left over, the part that doesn't die away, is called a steady state solution. Okay, and again, this will always happen whenever we have a negative a in our linear differential equation. We get a steady state solution. Now, here is a graph of that steady state solution, and it's just, you see, it's just a kind of a typical sine/cosine. It's a linear combination of the two, so we just get the typical periodic behavior. And this would be the solution if we were starting right at negative 2.4, if that was our initial condition. If that was our initial condition, actually, that yp starts there anyway, so our c part would be 0, and we wouldn't even have it. But what if we did have a different initial condition starting somewhere else, so that we would have the plus c e to the minus 1/2 t? So for example, let's add plus 2 e to the negative 1/2 t. Okay, so here you go. You can see this function doing very different things in the negative region, and it starts at a different place, and then it moves on. But you see that as time moves on, it converges to the steady state solution. It gets closer and closer to that. And just to do one or two more, different initial conditions will give us different c's. There's a c of 8 corresponding to an initial condition evidently of 5.6, and you see it comes from way up here, dips down, but then eventually follows the leader, follows that red one. I'll do a negative one, let's say negative 5. Yeah, so this one is going to be down here, an initial condition of negative 7.4. But over time, you see, no matter where they start, here, 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 or here, they all kind of end up doing the same thing. And that's that steady state solution represented by the original red one. Okay, so you can see that the differences between these going away, and the differences are these negative exponentials. And of course, that does go to 0. That does go away over time. So that's the concept of a steady state solution. The solution apparently forgets where it started, and it kind of doesn't matter. Pretty soon afterward, it does not matter where it started. The initial condition gets forgotten, and it just does this one kind of behavior.